This is just the polynomial x choose k minus 1. How did we not know that? I asked so many people, what is this sequence of pictures of? Well, this came up in a recent paper that I'm doing with some RUs, coefficients and roots of peak polynomials, where peak polynomials comes up in terms of permutations and the number of permutations for the given peak set. And we started factoring these things. They have lots of real roots, integer roots, and that's what's in this paper. There's a preliminary version on my website. Okay, what about this one? And I should say there are a couple of these where the authors are in the audience, so give everyone else a chance if you recognize it from your own paper. So what polynomials have these complex roots? Okay, now the author can speak. You recognize it? Maybe not. So these come from a beautiful paper of Devlin, Tycho, and Stanley. These are the zeros of Ehrhart polynomials, where there were like 100,000 random three-dimensional lattices. Take the Ehrhart polynomial, factor them, and draw the roots. There's some structure going on there, right? Those are not just randomly distributed in the complex plane. There's clearly some structure. And when I saw this one, it reminded me of another picture that I've seen similarly. So what polynomials have these complex roots? This came up as a piece of art in the joint meetings at the AMS recently. So this is done by Greg Warrington, and these are all the roots of all the Cauchy-linguistic polynomials for the Cauchy group H4, and then the shading, the coloring there is by density. Kind of similar, isn't it? It's oddly similar, sort of bat-like thing. And what about this one? What polynomial has these complex roots? And again, the author is in the audience.
Look and say problem.
Good, good. So these complex roots come from John Conway's polynomial of degree 71. Here's the, where'd my polynomial go? Oh, that slide got deleted somehow. I found the polynomial. It's degree 71. I used the version of it that's on the OEIS. Apparently the one in the paper has a typo. I learned that from the web too. The x to the 35 should be plus and not minus.
But do you have a picture with the typo?
I actually do on my computer. I just ran it. And you know, I couldn't tell the difference between the roots, because of course the x to the 71 dominates. But so what happens here is this beautiful, this is one that maybe is for the K-12 situation, right? The look and say sequence is 1, and then you read what you see. So 1, 1, and then you read the next iteration, you see 2 1s, and so on. So on each iteration you have a sequence. And what's the length? How does this sequence grow in length? Well, the size varies in a proportional to a constant. That's the Conway constant on Wikipedia. And that constant is very special and is the root of a polynomial, which is this degree 71 thing. So here's a sequence that, honestly, when I heard it the first time, I said, that's just like, that's really recreational math. Right? That's not even math. That's just, like, who made that up? But there's more to it than I could have ever imagined. And I learned about this from Jordan Edelberger's computer proof of the cosmological theorem, because somehow the proof got lost, I guess. And Doran gave a beautiful computer proof. This is a really perfect example of a computer proof for a mathematical theorem, because it's just the right length to wrap your head around. Okay, so who else is looking at zeros? Well, Richard Stanley has sort of started a new fingerprint database for theorems here. That's what I see going on. It's in its infancy. There's only a couple more to add to this list. I think there's 9 in there. But he started collecting this group of interesting polynomials and their roots, and he's including the PDF files, right, or the PostScript files. This is sort of how I think this database should go. I think it should be a collection of PDF files, and then you should be able to use machine learning to scan through these files and see what fits your picture the best, and then it points you back to the literature. That's where I see this going. But that's kind of a vague statement, right? So I'm thinking about this quite a bit. So what is the best way to fingerprint theorems characterized by applying a set of graphs? Maybe this is right, maybe there's other ways. Or what is the best way to fingerprint pictures of complex roots for interesting polynomials? Maybe they should be in two separate databases. I'm not sure putting them together makes sense, but maybe it does. So what's the best way to fingerprint any theorem characterized by pictures? And one of the things that Bridget and I talked about in our paper is what sort of gave Bridget the push, I think, to make this permutation database for permutation patterns when I was kind of stuck and thinking, oh my God, how's that ever going to work? How are you going to get started? I wanted to make it perfect. And she got started, and that's better. And it made me think of this quote from Rob Brooks. I used to work in his lab as an undergrad. He does artificial intelligence and robotics and things. And there was a whole movie called Fast, Cheap, and Out of Control, which was his mantra. And the idea is you just make your little robot as stupid and cheap as possible, make lots of them, make lots of mistakes, but you get something done fast. And so we have the same thing in front of us. So don't wait for the perfect fingerprint mechanism to start the collection. Get going with whatever you can. And I think that's what happened with the OEIS, right? It started out as a small sequence in a notebook, and it builds to something. You just have to start somewhere. So I'm going to revise those research problems for myself, for you too. It doesn't have to be the best way to encode pictures. We're really just looking for a good way to encode pictures and related theorems. Okay, so a very happy birthday to Neil and to the OEIS. 125 years combined, it's pretty amazing. And in particular, thanks for your contributions, Neil, both to the OEIS and also I think you're very kind in terms of helping me along the way with my questions and concerns and always answering emails. Somebody has to be there to make something like this work. And thank you to all of you for all of your contributions, because really this is such a worldwide effort. It's amazing. And I want to add one more thing. I decided to celebrate, or not celebrate, but observe Yom Kippur this year as a Unitarian. And that's what I am, a Unitarian who celebrates Jewish tradition. So I thought I should atone for my sin, which is I have not contributed to the OEIS financially. So who do I give this to?